from the City College of New York. My name is Saborn Barry, and today, welcome to lecture number 8. Let me just close this door. Of ordinary differential equations. So, today we'll be doing power series, but a little bit more advanced. So last time, you'll remember we did equations like these. Now, these equations are very easily solvable using the methods we've learned before. Separation of variables, the integration factor, undetermined coefficients, etc. So, it's a waste of time to use power series here. But now, let me introduce you to something different. What about an equation like this? Let me just make sure that whole thing's correct. An equation like this. Well, let's see what we can do. First of all, we've got a second order differential equation, so there's no separation of variables going on here. Additionally, for the same reasons, there's no integrating factor going on here. We've got non-integer coefficients. Undetermined coefficients only works when you've got these polynomial coefficients. So when we have things like these, undetermined coefficients just doesn't know what to do. And so, finally, variation of parameters could work, but variation of parameters, to get this, you actually have to know the homogeneous solution, which is what we're solving for right now. So variation of parameters isn't going to work here either. So what's our only choice left? Well, our only choice left, thank goodness it's carpet, is power series. Be equivalent to this power series. And then that means that y prime is equivalent to this power series. And y double prime is equivalent to this power series. Alright, so now what are we going to do? Well, we multiply y double prime by x squared minus 4. We multiply y single prime by 3x, and then we just have y. So let's actually get to doing that. So we get x squared minus 4 y prime is equal to the sum n squared minus n cn xn minus 4 times n squared minus n cn xn minus 2. Meanwhile, we get 3xy prime is equal to the sum of 3n cn xn. And finally, we just get ordinary y, which is cn xn. So now, let's sum these bad boys all up. We get sum of n squared plus 2n plus 1 times cn xn minus 4 times n squared minus n cn xn minus 2. So I can abbreviate this as n plus 1 squared cn xn minus 4 n minus 1 cn x to the n minus 2. So what's the pattern here? Well, it's not very obvious from this. So let's try summing it up and see if we can get any actual answers. So if we attempt to sum over this, what do we get? Well, we start with n equals 0. So we get 1 squared c0 x0 is just 1. So all of this goes away. Minus this whole thing gets zeroed because n is 0. So then you go to the next term, and the next term is where n is equal to 1, so you get 1 plus 1 squared, or 2 squared, times c1 x minus 4 times n minus 1 Cn xn minus 2. 4 times 1 times n minus 1, which means this thing actually gets completely zeroed as well. Alright then, so now we get to n equals 2, and finally this is where both terms come into play. So you get when n is equal to 2, this is just 3 squared times c2x squared and then minus 4 times 2 times 1 which ends up becoming 8 Cn, which becomes C2, x to the n minus 2 is just a constant term. So that means our constant term is C0 minus 8C2. So what's the general form of these terms, actually? Well, let's say we want the coefficient for the term x to the n. Well, that's going to be n plus 1 squared Cn minus, and now since this one has to catch up, I'm going to have to plug in n plus 2 into this term, minus 4 times n plus 2 times n plus 1, c to the n plus 2, x to the n. Oh wait, we can't include that part. Alright, so we've got this nice looking expression, nice looking. N plus 1 times n plus 1 times Cn minus 4n plus 8 Cn plus 2. And you can already see that working out over here. So, what does this end up becoming in the end? Well, you'll notice that every term has either only even or only odd. So we can form a relation between C0, C2, C4, C6, C8. And why is this huge? Because that means that C1 is equal to C3 is equal to C5 is equal to C7. Well, no, I'm just kidding. That's not true. So what actually happens when we plug in? So we get n plus 1 squared C0 minus 4 times n plus 1 times n plus 2 C2. So in this case, we can just erase all of the n's since they go to 0. So we get minus 4 times 1 times 2 is equal to C2. So we know that all of these terms have to be equivalent to 0. That means we can completely disregard this factor. So we get n plus 1 Cn is equal to 4 times n plus 2 Cn plus 2. Alright, and so what do we get at the end of the tunnel over here? That n plus 1 squared Cn is equivalent to 4 times n plus 1 times n plus 2 Cn plus 2. Now all you gotta do, cancel out these. So Cn is 4 times n plus 2 divided by n plus 1. Cn plus 2. So what does that tell us? Well, C0 is equal to 4 times 2 over 1 C2. C2 is equal to 4 times 3 over 2 C4. C4 is equal to 4 times 4 over 3 C6, so on and so forth. Do you see the pattern? This is some telescoping series stuff. 2 times 1, 2 over 1 times 3 over 2 times 4 over 3 times, if we're continuing up to C sub 2n, then we get, well, what do we get? C0 gives us 2, C2 gives us 3, C4 gives us 4. So what pattern can we deduce from that? Well, we get that C sub 2n is equal to 4 times n plus 2 divided by n plus 1. Wait a second. So this is not true, actually, I believe. Yeah, it is true. So we have 2 over 1 plus 3 over 2 plus 4 over 3 plus dot 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 times n plus 2 divided by n plus 1. And at the end of the day, this is all going to telescope out and become n plus 2. So at the end of the day, we should get that C0 is equal to n plus 2 times 4 to the n. Am I doing this correctly? I feel like, yeah, I should be doing this correctly. Is equal to n plus 2 times 4 to the n plus 1 Cn. Alright, so let's try an example. If we have, let's actually invert this formula to get C n plus 2 is equal to 1 over 4 n plus 1 over n plus 2 Cn. Okay, so now what do we do? Well, all we have to do is just continue the pattern. Cn plus 4 is equal to 1 over 4 n plus 3 over n plus 4 times Cn. But wait, what do we do now? Cn plus 2. But what do we do now? Well, we can just plug right back in Cn. Alright, and then Cn plus 6 is equal to 1 over 4 cubed n plus 5 n plus 3 n plus 1 over n plus 6 n plus 4 n plus 2. So what are we getting at the end of the day? Cn plus 2k is equivalent to 1 over 4 to the k minus 1, as you can see over here. Since k here is 2, 2 minus 1 is 1, so we've just got, shoot, this is just k, oops. So we've just got k over here times this endless product. I feel like I'm messing something up. No. Okay. Times this endless product that we have over here, which is n plus 2k, n plus 2k minus 2, dot dot dot, n plus 2. And on the top, meanwhile, we have n plus 1, dot dot dot, n plus 2k minus 3, n plus 2k minus 1. So now, here's the magic part. Plug in 0 for n. Now we get that C2k, this is the end, Cn. C2k is 1 over 4k, 2k minus 1 over 2k. 2k minus 3 over 2k minus 2. Dot dot dot. 1 over 2. And eventually we get C0 on this other side over here. So what is the solution at the end of the day? Well, so we've got every even term solved. C0, C2, C4, C6. That's all well and good. But now we have to figure out C1, C3, C5, C7. But hey, it's mostly the same exact story that we saw all the way over here. It's exactly the same thing. So all I'm going to do is just copy that down. So we've got C0 plus C1x plus 1 over 2 C0x squared plus 1 over 2 C1x cubed plus 1 times 3 over 2 times 4 C0x cubed plus 1 times 3 over 2 times 4 C1x cubed. Wait. C1x to the 4th. Wait. Oh, sorry. And so on and so forth. So what do we get? Well, you'll notice we can factor out C0 plus C1x from this entire expression to get 1 plus 1 over 2x squared plus 1 times 3 over 2 times 4 x to the 4th, and so on and so forth. So what's going on here? Well, we've just got C0 plus C1x times a specific sum, which looks very cool because 1 times 3, we've got 1 times 3 times 5, 1 times 3 times 5 times 7. These are like factorials, but missing all their even terms. So this is like 8 factorial divided by 2 times 4 times 6 times 8. But wait, this looks like just a factorial, but every term is multiplied by 2. This is just 2 to the 4 times 4 factorial, right? So this is 2 factorial over 2 to the 1 times 1 factorial. This is 4 factorial over 2 to the 2 times 2 factorial. This is 6 factorial over 2 to the 3 times 3 factorial. All connects together. So we've got the sum of C0 plus C1x times 2n factorial divided by 2 to the n times n factorial x to the 2n. Is that correct? Indeed it is. So that's it. That's the huge behemoth of an expression. You might ask before we go, hey, wait, last time there was only one constant. Why are there 2 this time? Well, that's exactly because we've got a second order differential equation right here. 1, 2, 3, 2 derivatives. Since we've got a second order differential equation, we have no choice other than to expect 2 constants. So, yep, that's it.
What do you see?
Sand.
Imagine if we could look so closely, we could see each grain, each particle. You see, there are patterns in everything.
Integrals, infinite series.
I've never seen anything like them. From an Indian